Good morning. My name is Jim Lyng, and in this very short presentation today, I'm going to talk very briefly about electroprocessing of food. So the importance of electricity in a sustainable future is really impossible to ignore. It's evident when you go into a shop and buy an electrical appliance. It's evident in the increasing number of solar panels, wind turbines, and electric vehicles we now see driving on our roads. It's evident when you turn on your TV and you see adverts such as a new air grid ad or shows such as What Planet Are You On? And at the present time, there's so much interest in electricity that even Hollywood have released not one, but two movies on the history of electricity in the past 6 months. In today's presentation, I'm going to talk to you about the direct application of electrical current to food. Now, this form of electroprocessing eliminates inefficiencies as you're using the electricity directly. It also induces two phenomena, one of which is known as electroporation and the other of which is known as electroheating. Now, to illustrate the difference between these two phenomena, I'm going to put up a liquid system into which I'm going to place a solid food, in this case an apple as an example. We're going to pass electrical current directly through that system, so I need a pair of electrodes to come in contact with that system. I'll also draw your attention to the fact that in the food and the surrounding liquid, there are a large number of dissociated ions at this point in time, and these are randomly dispersed throughout the system. However, when we apply an electrical current, these ions begin to mobilize themselves and orientate themselves appropriately in the electrical field and follow the field through the food. This can be used for applications such as impregnation of cryoprotectants, impregnation of brines, to enhance extraction from food systems, to accelerate dehydration of food systems, and if the movement of ions causes the formation of pores in microbial cells, it can be used to inactivate microbes and even soften textures in food systems. And this phenomenon is known as electroporation, where pores are induced in foods due to the passage of electricity. If sufficient electrical energy is applied, you get a substantial amount of heat generation in the food system, and this phenomenon is known as electroheating. In terms of direct application of electricity to foodstuffs, there are two categories that I'm going to talk about today: high voltage pulse electric fields and moderate electric fields. These technologies differ in three respects. Pulse electric fields involves the application of higher field strengths than moderate electric fields. Pulse electric fields involving field strengths in excess of 0.7 of a kilovolt per centimeter, while moderate electric fields involve lower field strengths of less than 0.7 of a kilovolt per centimeter. Pulse electric fields is applied in short pulses, while moderate electric fields are applied continuously as sine waves. And pulse electric field generation is more complex because it involves capacitors and pulse forming networks to form these pulses, while moderate electric fields just involves simple AC application to foodstuffs. In terms of what is known about these technologies, there's also a difference. If you look at the scientific literature for the past 30 years, there are about 500 papers which fall under the heading of moderate electric fields. But there's about 4 times that number on pulse electric fields. So a lot much more is known about this technology. If you look at this diagram, this red line shows the demarcation between pulse electric fields, which is above the red line, and this red line is 0.7 of a kilovolt per centimeter. Below the red line, we have moderate electric fields. And so much is known at this stage about pulse electric fields that field strengths and energies that are required for microbial inactivation, for sludge disintegration, for improvement of mass transfer, for permeabilization of biological cells, and for induction of stress response in plant tissues is very, very well known. By contrast, MEF is not nearly as well defined as yet. I'm going to give 2 examples of PEF applications in food processing. The first is in the area of shelf life extension in beverages. And this basically, the basis of this is that electroporation can be used to inactivate microbial cells in a non-thermal way and produce a high quality beverage at the end of the day. Now, this is TRL9 stuff. It's available and in use in industry in the present time. The image in the lower left-hand side of the slide shows the system that we currently have in our labs. This next diagram I'm going to show you shows the impact of pulse electric fields on freshly squeezed juices. And you can see the untreated juices, you can see the rapid increase in microbial load within the juices. By contrast, the pulse electric field treated systems have a considerably lower rate of microbial load increase, and you can see that shelf lives in excess of 21 days are very achievable with this technology. This has huge benefits for retailers because it means they don't need to mark down prices as products come close to the end of their shelf life. It's also very useful for processors because it allows them to get greater market reach for their product. And also it means they can tidy up their production schedules because they don't have to kind of break up the day and produce different products at different times during the day. And this technology is, as I said, in use commercially. There are European companies using it, and there are products on supermarket shelves in Europe that are processed with this technology. Yesterday, I checked with Alea, one of the leading manufacturers of these systems, and they currently have 15 commercial scale systems in operation worldwide at the present time. The second example I'm going to give you is the use of pulse electric fields in potato softening as part of a French fry manufacturing process. Now, by contrast with the shelf life extension in fruit juices, there's about 120 commercial systems in use worldwide and another 35 systems currently under construction. Now, if we look at this in high volume production of French fries, where you're talking about processing tonnages of potatoes of up to 50 tons per hour, French fries are cut in what's called a hydrofoil, which basically is a high velocity jet of water which forces the potatoes through a slicing grid. Now, if you try to do this without a softening pre-treatment, the fries split and break, and it's not very successful. So the standard preventative measure involves soaking the potatoes for 30 minutes in 60° C water. But this is incredibly energy intensive, uses a significant amount of water, and you lose quite a lot of starch from your potatoes as a result. Some years ago, it was discovered that this soaking treatment could be replaced by a low energy pulse electric field treatment that had the same effect. And by applying 1.8 kilovolts per centimeter, 40 pulses of pulse electric fields, you got the same softening effect, and manufacturers were able to eliminate this soaking step from the manufacturing process. This was very scalable, up to 50 tons per hour, so it really was a no-brainer for industry, and it's really become, to be honest with you, at this stage, it's nearly the industry standard in the French fry industry. There are many other examples of pulse electric field processing that I could talk to you about today. We have a lot of work ongoing in UCD, and there's work going on elsewhere, but suffice to say, you're likely to see considerably more applications for this technology in the years ahead. The second area I want to talk to you about is moderate electric fields, and today I'm going to specifically focus on the use of this technology for electroheating. This technology, when applied in this way, does two things. It basically lends itself to green heating and process intensification. Now, moderate electric fields, basically, when it's used for heating, it allows direct conversion of electrical energy to heat, and you can get up to 95% of your electrical energy ending up as heat in your foodstuff, compared to maybe 50% by conventional means. So it certainly fits in with the concept of green heating in an efficiency sense. It also lends itself to volumetric heating of large product masses. So continuous processing of products such as large diameter meat products is certainly possible, and that lends itself to process intensification and increasing throughput through production lines. I'm going to give two examples today of moderate electric field applications in this way. The first is pasteurization of shrimp, where in this work we were working with a Danish company, and we're looking at electroheating shrimps to temperatures in excess of 72°C. The big problem with the conventional method they use is that the tail, the body, and the head of the shrimp heat at different rates. So you get big variation within the shrimp. You overheat the tail while you're waiting for the body to reach the target temperature. And very quickly, we found that due to the volumetric nature of MEF heating, you got a much more uniform heating with the head, the body, and the tail heating in a uniform way. And this was evident within shrimps, but even when we compared large shrimps and small shrimps, the variation between shrimps was considerably less, and the uniformity of heating was considerably greater with the moderate electric field process. Now, we took this to TRL5 at the time, and if the technical manager at the company had his way, we probably would have taken it further. But the brakes are on this for now, but I'd say it's an area we're very likely to come back to again in the future. The final area I'll mention to you is the pasteurization of meat and solid foodstuffs. And this is an area that we've worked on for many years. We've done a lot of work on fundamental issues such as conductivity and the distribution of conductive ingredients and their impact on heating uniformity. We've looked at the impact of food structures such as intramuscular fat and comminuted fat on current flow and uniformity of heating. We've done a lot of modeling in conjunction with other partners on the environmental impact and the role it plays in heating uniformity. We've worked on packaging of foods, and we're now at a point where we can MEF process products in a sealed package, which is commercially quite significant. And we've now reached a point where we have two very nice pilot scale systems, and we have a project which will be running for the next couple of years, and we hope to take this technology further in terms of its application to meat and other matrices in the next few years. So similar to PEF, we've a considerable amount of research ongoing in this area, and there's also a considerable amount of research in MEF technology going on elsewhere. And suffice to say, it's very likely that you're also going to see many more applications for this technology in the years ahead. So to finish off, in terms of future prospects for MEF and PEF technology, both of these technologies really fit in with the concept of green processing. However, they're niches, and they find niches where they will achieve their true potential. And it's sometimes difficult to say where these niches will be. If you ask me 10 years ago, would potato softening be have greater commercial uptake than beverage preservation using PEF technology, I probably would have found that difficult to believe. But today, that's the reality, that the niche, a more successful niche for PEF is in the softening of potatoes. So in conventional processing, really, for industry to consider taking up these technologies, it really has to be a no-brainer. It's not sufficient that they give marginal gains. It has to be substantially superior to the conventional process. However, in future processing in areas such as the bioeconomy and so on, the sustainable nature of these technologies fits in with that ethos, and it's likely that there will be more of a future for these technologies in that area. But for now, we as researchers are really the custodians of these technologies, and it's vital that we continue to do research on them and find other applications for them for the future. Thank you very much for your attention today.